In this lesson, we're going to talk about continuous random variables, how to find the probabilities, and how to find expected value and the variance for this kind of random variables. Now, the first thing I would like you to do is try to remember the things that we did for discrete random variables. We were creating a table where each of the values of the variable were able to be represented by one specific outcome, and we were able to associate specific values of probability for each of those outcomes. One of the representations that we could do for that information was the table, but also we could do histograms. So whenever we did the histogram, it would look like what we have here on the screen. Now, this histogram, we can think of it as the collection of all the bars whose height is the probability value, and the width, let's say, is going to be 1. Overall, the probability for each of those outcomes would be represented by the area of each of those bars. Now, that's a very important concept because it's going to help us transition from a discrete variable to a continuous variable. The probability for these discrete variables is represented by the area of each of these bars. Now, one way to transition into continuous variables would be to think about we are collecting data. Therefore, we are able to create classes, like the width of each of these bars, a little bit more snug. So if we reduce the width of each of these bars, then we are able to get a more detailed view of how the probability is represented. And this is something that we can do if we just collect more and more and more data about the experiment. And so when we reduce this, the width of the columns, we can still think of the probability as the area of each of the columns, but what we can see is that the total area has to be 1 because we're talking about probabilities. The sum of all of the areas of each of these bars has to add up to 1 because we're talking about probabilities. So that means the area under this curve has to be equal to 1. We're going to call this function f of x the probability density function. And like we said before, the integral of this function is going to give us the overall probability. This leads to one very important difference between the continuous random variables and the discrete random variables. For discrete random variables, we were able to determine the exact probability that one of the outcomes is going to have. When we're talking about continuous random variables, in the limit when this distance or the width of each of the classes goes towards 0, that means the area of the individual rectangles goes towards 0. So it's not going to be possible for us to give a value of probability specifically for each individual outcome. Since we have an infinite number of outcomes, it's not possible to do this. So the way that we're going to calculate probabilities is going to be through integration. In summary, let's consider x a continuous random variable that has a probability density function f of x, where the function is defined between the interval a to b. The first outcome that we got is that for a specific value, x sub 0, within that interval, the probabilities that x is going to take that specific value, x sub 0, is going to be equal to 0. Another outcome that we got from the previous discussion is that the area under the curve over the whole interval or domain of the function f of x is going to be equal to 1. The third outcome is going to be related to the probabilities. We said that if we wanted to calculate probabilities, we would need to find the area under the curve for a given interval. So the probability that x is going to take values bigger than c and smaller than d is going to be given by the integral from c to d of the function f of x with respect to x. This is provided that the values c and d are within the interval of the domain of the function. Let's consider the first example. F of x describes a random variable x and is defined as this piecewise function that we have. Here, verify that f of x is a probability density function, and b, find the probability that x takes values between 5 and 8. So the way we're going to do A is checking that the integral between 2 and 10 is equal to 1. So we have to evaluate the probability from 2 to 10 as the area under the curve of the function f of x. Now from 2 to 10, this integral is going to be 1 over 512, 12x squared minus x power 3 minus 20x with respect to x. This is equal to 1. Therefore, it is a probability density function. Now, to find b, the probability that x takes values between 5 and 8, we need to calculate the integral from 5 to 8 of f of x with respect to x. And if we use our calculators, this integral is going to be 1161 over 2048, or 0.5669, which if we write in three significant figures is 567. Now let's see how we can calculate the expected value and other statistical quantities for a continuous random variable. In terms of the expected value, the way that we calculate the expected value for a discrete probability distribution is by taking the sum of the products of each of the outcomes times their probabilities. In the case of a continuous random variable, this sum is going to be taken the limit and it will become an integral. And the integral is going to be calculated over the domain of the probability distribution density function. So this is going to go from a to b of the variable x, f of x, with respect to x. Now this should give us the expected value. Then we have the mode. In the case of a discrete random variable, the mode is going to be the value of x that has the largest probability value. In the case of a continuous random variable, the mode is going to be the value of x for which the probability density function will have a maximum. For the median, we have in a discrete probability distribution, the median is going to be the middle value or the value of x such that the cumulative probability function first reaches an amount bigger than or equal to 0.5. In the case of a continuous distribution, the value of the median is going to be the value of x such that the probability calculated through the integral will have a value of 0.5. We can also calculate percentiles. In a discrete random variable, we would calculate the percentiles in a similar way as we calculated the median. So the median would be the middle value, and so the term, depending on what percentile we're trying to find, we need to calculate the corresponding probability value. For example, if we're trying to find the 25th percentile, then we should, instead of finding the value of x for which the probability first reaches 0.5, we need to find the value of x for which the probability first reaches the value of 0.25. So depending on the percentile, you're going to do a change in the probability value for the value of x that you're looking for. In the case of continuous, you can do exactly the same. You are going to find the value of x that accommodates to that percentage of probability. Finally, for the variance, we've been using the expression variance is the expected value of the squares minus the expected value squared, and that is exactly the same expression that we're going to use for the continuous random variable. In this case, the expected value of the squares is going to be calculated as the integral over the domain of the probability distribution function of x squared times f of x with respect to x. Let's work a second example. The continuous random variable x has a PDF f of x where it's given by this piecewise function. Sketch a graph for f of x, find the value of k, find the mean, median, and standard deviation, and find the interquarted range for this distribution. Let's begin with A, sketch a graph for f of x. There are going to be three sections to this graph. The first section is going to be an increasing line from 0 to 1, then a section of a quadratic from 1 to 2, and then from 2 to 4 we should see a line with a negative slope. We don't know the value of k, so we are unable to fit values to the y-axis, but we know that the behavior has to be something similar to this. Now, in order to find k for B, what we need to do is we need to make sure that the area under the curve is equal to 1. So for that, we need to calculate the integrals for each of these intervals. So the 1 has to be equal to the integral from 0 to 1 of 2k x with respect to x plus the integral from 1 to 2 of 2k x squared dx plus k 12 minus 2x plus the integral from 2 to 4 of k times 12 minus 2x with respect to x. This can be simplified a little bit if we take the k out as a constant common factor, and we can use our calculator to calculate these integrals, leading to a value of k equals to 3 over 53. Now we want to find the mean, the median, and the standard deviation. For that, we are going to start with the mean. The mean is going to be the integral from 0 to 4 of x times the function f of x with respect to x. Again, we have 4 different integrals that we need to do, and we can just do those quickly with our calculator, leading to an expected value of 2.42 to 3 significant figures. Next, we're going to do the median. For the median, let's call it m, we need to find next we're going to do the median, let's call it m. So we need to calculate the integral from 0 to m of the function f of x with respect to x, and make sure that this is equal to 0.5. I've gone ahead and calculated the first 2 integrals, and you can see that the cumulative probability for the first 2 pieces of the function are 3 over 53 and 14 out of 53, which means the cumulative probability for these 2 sections is 17 out of 53. That's not yet 50%, which means the median is going to fall in this third category. So we're going to focus on that integral. So what we need to find is the integral from 2 to m of 3 out of 53 times 12 minus 2x, such that this is equal to 19 over 106, which is what is left to complete the 0.5. Using your calculators, you can find that m will take a value of 2.42 to 3 significant figures. Next, for the standard deviation, we need to find the expected value of the squares, and then take the value that we found for the expected value and square it. And when we take the difference, we will get the variance. And now that we have the variance, to find the standard deviation, we just need to take the square root of this result. And the standard deviation is going to be 0.859, correct to 3 significant figures. Finally, for D, we need to find the interquarted range of this distribution, meaning we need to find the 25th and the 75th percentile. From our calculations in C, we can know that the first quartile is going to be in the second function. The first piece of the function has a cumulative probability of 5/53. So we will need to add that to the integral in the second So based on the information that we had for the previous parts, we know that the first quartile, 25%, is going to fall in the second piece. So the expression we can write to find that quartile is going to be the integral from 0 to 1 of 6/53x with respect to x plus the integral from 0 to m1 of 2 of 6/53 x squared with respect to x has to be equal to 0.25. Now we already know the value of the first integral. The first integral is 3/53. So we just need to focus on finding m1 using the second integral. So by rearranging this expression and solving for m1 using my calculator, I find that the lower quartile or the 25th percentile is 1.83. Now I'm going to repeat this process, but for the 75th percentile, you can check all of this process by following along and trying to solve these equations by yourselves as well. You can do it by using technology, like I did here. I used my graphic display calculator, and by doing so I find that the value of m2 is 3.10 to 3 significant figures, which would mean that the interquartile range for this distribution is going to be 3.10 minus 1.83, and that is equal to 1.27. And again, this is also to 3 significant figures. Now it's your turn. For the probability density function that I am presenting you in here, can you try to find the information that I'm asking in A, B, C, and D? Let me know how you do in our next class.